So we're here in one of our glasshouses where we're looking at our upper canopy blackleg resistance experiments for 2021. So with upper canopy, with GRDC Investments, we've been working for a number of years on really working out what is upper canopy, what causes it, and then management plans for growers, such as timing of flowering and fungicide application. But really the missing ingredient has always been the genetic resistance for upper canopy, and this has been a real big issue for everybody. For instance, we don't know what returns growers are going to get because we don't know what the resistance is of their individual cultivars. But before we can do any of that work, what we need is a screening methodology, a high throughput, highly reliable screening methodology. Once we've got that, then we can help the seed companies breed for resistance, and we can also independently screen all the cultivars and hopefully produce upper canopy blackleg resistance ratings. And then we can give farmers advice on their cultivars and if those cultivars need protection with fungicides in particular regions and seasons, etc. So that's really the key thing. And that's the investment that we've been working on for the last 2 years. And we've made a lot of progress. We're certainly a lot higher throughput than what we were, and we think we've got some good reliable methodologies. So what this experiment doing is repeating some of the work we did last year to show that it's repeatable, but also to actually look at choosing new isolates. So we're screening a whole range of blackleg isolates, which we hope will then eventually form a differential set. So we'll have a standardised set of isolates which we know can discriminate for genetic resistance. Now the method we do is a scrape method on the leaf nodes, so we can create a wound, and we found one a moment ago here, and I think Ange has just found it again. So we do a scrape with a scalpel, put a drop of inoculum on it, and then it sits there in that leaf axil area, and we get the infection. We then wait for a period of time, and then we can slice the plant open and then measure the length of that lesion. And last year showed that we could get really good differences between cultivars by doing that. And hopefully if we have a range of isolates, which we know how they react, we can then create a screening system which is really reliable. And the other thing with this screening system, we're doing it in the glasshouse because it has to be independent of flower timing. We know in the field flower timing causes a lot of disease escape, so we have to come up with a system which is totally independent of that. So that's what we've got. We've also, last year, we identified some lines which we think might be resistant and ones which we think might be susceptible. So in this screen here, we've really extended the number of cultivars that we've got based on the data from last year. So by the end of this year, we hope that we'll have resistant controls, susceptible controls, and we'll have developed differential isolates. If we put that whole package together, hopefully next year we'll be in a really good place to actually start screening germplasm and then really turning it into a high throughput system. And if we do, that'll be a major outcome and just a really great breakthrough, I think, for the industry for moving forward. So one of the things with upper canopy resistance is, as I said before, we think we've identified lines which are resistant and ones which are susceptible, which will be fantastic for our controls when we start routine screening. But one of the big things we've got to make sure with this resistance is that it's stable across years and environments. So what we've done is we've taken which we think are our best control lines, and we're just screening them a whole range of different environments to make sure that resistance is always resistant. And it's also not dependent on flower timing. So you can see here in this experiment here, we've got these different cultivars which we think we know what they are, and they're flowering at different times and whatever, and we're hoping that over all these different environments, different sowing times, etc., that resistance will always be resistant. And if we can achieve that, I think we'll have a really good tool to go to the breeders with.
Okay, so in here we're looking at both upper canopy infection and crown canker resistance. So last year we had some preliminary data that suggested that crown canker resistance, or quantitative resistance, is actually expressed throughout the plant, not just at the crown, and it gives some protection towards upper canopy infection. So what we wanted to do is to test this theory. We're going through and screening a range of cultivars with a range of isolates, and we're inoculating them both at the seedling stage to give us some crown canker results, and also coming back and then rescreening those same plants at the 30% bloom stage to look at the amount of infection then again at that growth stage. So essentially what we've got is a range of plants that have been inoculated at the crown, and they are starting to get some crown infection. So you can see we've got this cultivar here that has a susceptible reaction happening at the crown canker infection. And then we've come back and inoculated at 30% bloom, and we can see that lesions are starting to develop again. Then we've got this second cultivar, which has been inoculated with the same isolate, but we've got a higher level of quantitative resistance, so we're not seeing any crown canker develop, and we're also seeing less upper canopy infection starting to develop. So we've got around 30 different isolates being screened and a range of different cultivars, and so hopefully we'll have a wealth of knowledge at the end of this to work out whether this quantitative resistance and upper canopy infection is the same response. So to get the full picture of what's happening with quantitative resistance, we're also using a universal susceptible control. So this is our West Star here. It's been inoculated at the seedling stage with the exact same isolates as those guys over there, which are our Australian cultivars. And you can just see what improvements we have made, because this is our susceptible cultivars, and you can see there is not going to be much left by the end of the growing season, versus our Australian cultivars, which, as I said, have been inoculated with the exact same isolates and look relatively healthy. So the Australian breeders should pat themselves on the back. Okay, so in here we're doing all of our R genotyping work, or resistance genotyping work. So this is for programs 2 and 3. So program 2, we characterise all the commercial cultivars for their major resistance genes, and we do that through a combination of phenotyping with differential isolates and using molecular markers. And then for program 3, we're looking at novel sources of resistance. So again, using the isolates to look for differential reactions that we haven't seen before. So this is all of the work that's undergoing at the moment. Here is an example of what we look for. So here we have a susceptible reaction, so you can see nice big lesions developing, and right beside it here we have another cultivar inoculated with the same isolate, where you're seeing a nice resistant reaction with no lesions formed. So that's what we look for overall, and we put all the data together with the molecular markers and then provide that to industry.
Blackleg populations are really diverse across Australia, from region to region, year to year, and it's really dependent on what cultivars people have grown in the past. One of the things we're doing is we're screening the most diverse populations from across Australia, across a whole range of different germplasm. And this data can then be used to advise farmers on what populations are prevalent in their regions, but also it's a really good tool for the seed company, so that if we get the most virulent populations from across Australia, we can screen their germplasm with those populations, and then they know that they're going to stand up in future years. So if you look at these experiments here, we've got plants here which have been inoculated in what we call our tub screen, ascospore showers with stubble, and you can see some cultivars or genotypes already getting stubble, whereas genotypes next door are looking quite resistant. And this is the massive diverse population. So in this one experiment here, we've got the 6 most diverse blackleg populations around Australia. We can do it in one screen and provide that information both back to industry and both back to the seed companies. The other way that we monitor our blackleg populations is through our field sites. So across Australia, we've got 32 field sites which are sown alongside the MVT canola trials. And in those sites, we have different cultivars which have got different major gene complements and different quantitative resistance. And when you have all those cultivars side by side, you can obviously see the differences in the amount of disease they're getting, and that will then relate back to the population which is prevalent in that particular region. So we use those sites already to put out warnings for resistance breakdown. So we put out a warning earlier this year that the group H resistance, which is a brand new resistance gene, was breaking down in the high rainfall zones where they'd been using grain and graze. However, it was totally stable in all the other regions, so it was just something for those growers. We've also seen some of the D resistance starting to show disease this year, so farmers have been therefore putting more fungicide on this year because they're getting concerned that resistance being overcome. The group B resistance has really been overcome, and that's really because some of the group B hybrids have been fantastic over the last few years. So again, the farmers now know they can grow those cultivars for high yield, but also have to put a fungicide on. Whereas some of the other resistances, the F-type resistance, etc., and some of the A resistance are standing up really well, so farmers know they don't have to worry so much about them. So that's the 32 monitoring sites, and we also use those sites to collect the populations that we use to screen these tub screens as well. When it comes to research on cultural practices by farmers, one of the big changes over the last few years has been that farmers have gone to this satellite guided sowing system. So full stubble retention, standing stubble, sowing between the rows, etc. And this actually has a big impact on diseases such as blackleg because they're stubble-borne diseases. So you change the way you deal with stubble, you change the way the disease works. And what we've discovered over the last few years by monitoring spore release from stubble, from standing stubble, lying stubble, and stubble from different ages, is that these farming practices have actually changed the way spore release occurs. So we now know from counting spores the last couple of years that we get more spores released from lying stubble than standing stubble in the first year, and the standing stubble, so the full retained stubble, also releases spores later in the year. So it stays drier during the growing season, then releases spores later in the year. And we think this has ramifications then for things like upper canopy. So it might be a reason why we might get less disease at the crown canker stage and more disease at the reproductive stage. And then for that has ramifications for breeding companies, for where they put their resources in resistance, and fungicide companies and fungicides timings and stuff like that. So we've got that great data, but one of the things we don't have is how do you relate spore release to actual disease on plants? Because you can't just go and tell farmers to change their practices because we've changed spore release. We actually need evidence that it will change plants. So we've done a whole range of experiments this year where we've done just that. We've got standing stubble, lying stubble, 1 year stubble, 2 year old stubble, and then we put plants in, sown early to get upper canopy blackleg infection, and then sown late to get crown canker. And you can see there's our 1 year old standing stubble, and we come over here and we have the 1 year old lying stubble, and we're seeing quite big differences in disease pressure now. And we've also done this with different quantities of stubble too. So you can see a low to stubble there and high, and then I said with the 1 and 2 year stubble as well. So it's really more of a methodology experiment, but we really want to actually show that changes in stubble practices, changes in spore numbers will actually influence how much disease we get.